This is the last exercise of this section, number 8. In it, we first define a new function lambda for all positive integers n. When n is 1, lambda is defined to have the value 1. That means lambda of 1 is 1. And if n is greater than 1, then you already know by the fundamental theorem of arithmetic that n has a canonical factorization, a prime factorization, where again you know these things, that these primes pi are distinct and the exponents ki are all positive integers. So there is no need to write those things again. In this case, this is the definition of lambda. Lambda of n is minus 1 to the power the sum of the ki values. Now we have to prove two identities involving this function lambda. The first of which is this: summation mu of d times lambda of d, as d varies over all the positive divisors of n, equals 2 to the power omega of n. What is omega of n? Omega of n is the number of distinct prime divisors of n. For example, if this is the factorization of n, then omega of n is equal to r. We are going to see part B afterwards. Let us first prove this one. We start the solution by considering the case n equal to 1 separately, and our remark is that this case is trivial, that in this case the identity is very easily seen to be true. Let's see how. How many elements does this sum have? Elements means term. How many terms are there in this sum? There are as many terms in this sum as there are positive divisors of n. So when n is 1, there will be only one term here, because 1 has only one positive divisor, which is itself. And that only one term will be mu of 1 times lambda of 1. Mu and lambda values are both equal to 1 when the input is 1. So the left hand side is 1 when n is 1. What about the right hand side? Omega of n is the number of prime divisors of n, distinct prime divisors. The number 1 has no prime divisor. So omega of 1 is 0. So the right hand side is 2 to the 0th power, which is also 1. So that means in this case, yes, we are having equality. And now we are going to consider the other cases where n is greater than 1. So by exercise 3, in place of this sum, which is the left hand side of our identity, we can write this product. But the question is, why? Why are we able to use exercise 3 in the first place? In exercise 3, if you go back and see what it was, there was a general multiplicative function f here. Here we had mu, but here we had f. And the exercise tells us that you can write this product. So that raises the question about the multiplicative nature of lambda. We have just now seen what lambda is. We have defined lambda here, right? Do we know lambda is multiplicative? Actually, we should know. We should know in the sense that this is not where we define lambda. Lambda is defined in the previous exercise, exercise 7, which I left to you. So there actually lambda is defined for the first time, and there one of the things the exercise asks us to do is to prove that lambda is multiplicative. So I am assuming that fact here, assuming the result of exercise 7. On that assumption, we can use exercise 3 and write in place of this sum, this product. Now what do we have in this product? Each factor is 1 minus lambda of pi, a prime in the prime factorization of n. What is lambda of p1? What is the prime factorization of p1? That is p1 itself. And what is the exponent that we have here? What is k1? 1. So that is why by definition lambda of p1 is minus 1. Minus 1 to the power k1 plus k2 up to kr, that thing. All the factors are like that because each one is lambda of a single prime. And these factors are just 2. How many 2's? As many primes there are, namely r. so 2 to the power r. But r is omega of n because omega of n is the number of prime divisors, distinct prime divisors of n, which in this case is r. So that's how we have our first identity proved. Now let us see part B. The identity in part B is this. Again another sum where d varies over all the positive divisors of n, and the general term is this, lambda of n divided by d this time, times 2 to the power omega of d, and we have to prove that no matter what n is, the right hand side is always 1. So we start the solution slightly strangely by naming the entire left hand side f of n and noting the fact that it's a function of n. I mean, of course, we have to prove that it's always 1, but fundamentally this sum depends on n, and that's why we have named this function f. So that means we have to prove that this capital F is the constant function 1, that no matter what the input n is, we always get 1. Now it's a bit difficult to work with a general n, because a general positive integer n has many positive divisors, and it's difficult to figure out what the positive divisors are. For example, if you think of an n which is greater than 1 and say its prime factorization has r distinct prime factors with arbitrary exponents, just imagine how many distinct positive divisors that number will have. It's a large set. So the sum will be complicated and we will get lost. Instead, to reduce the complexity, we make this observation. We claim that our function f is a multiplicative function. Let us first prove this claim and then we will see how it helps us to make things simpler. So to prove that f is multiplicative, of course, we have to take two positive integers m and n such that their GCD is 1. That means they are relatively prime. And then we have to prove that f of mn, the product, is equal to f of m times f of n. That will mean that f is multiplicative. Now before we start our calculation, to show that, we note something that we saw in a previous result. We know that in this situation, any positive divisor d of the product mn looks like this, is uniquely expressible as a product itself, d1, d2, where d1 and d2 are also positive integers. d1 is a divisor of m, d2 is a divisor of n, and they are also relatively prime, just like m and n. And now let's start calculating f of mn. So we start our calculation. Yeah, it looks scary, but let's try to understand the steps. First we write what f of mn is. We use the formula, the definition of f. So in that formula, in place of n, we just have mn. That's it. In the next line, we use the fact that the positive divisors d of mn look like this, d1, d2, where d1 is the positive divisor of m, d2 is the positive divisor of n, and d1 and d2 are relatively prime. So we replace d with d1, d2. That's what we do in this step. In the next step, we of course keep this condition as it is for now, and we write this ratio slightly differently as m divided by d1 times n divided by d2. Note that these two are integers because d1 divides m and d2 divides n. Now how is omega of d1 d2 equal to omega of d1 plus omega of d2? Let's take one small example and then we will think of the general case. Say d1 is 2 and d2 is 3. Do not forget that d1 and d2 have to be relatively prime. So d1 d2 is 6. What is omega of d1 d2? Omega of 6, the number of distinct prime divisors of 6, which is 2. there are two distinct prime divisors of 6, 2 and 3. What is omega of 2? 1, because 2 has only one prime divisor, which is itself. Similarly, omega of 3 is also 1. 2 is equal to 1 plus 1. What will happen in the general case? Did you see why these two are equal? Say you have a general d1 and general d2. On this side you have d1, on this side you have d2. d1 has a prime factorization. d2 also has a prime factorization. Because they are relatively prime, this set of primes is disjoint with this set of primes. There is no common prime common to both the sets. Now, if you take the product of d1 and d2, these two prime factorizations come together and give us the prime factorization of d1, d2. And because there is no common prime, they just simply come together. So, if d1 has a given number of distinct prime divisors and d2 has a given number of its own distinct prime divisors, and there is no common prime divisor, so d1, d2 automatically will have how many prime divisors? The number of prime divisors of d1 plus the number of prime divisors of d2. That is why we have this. Alright. Now the next step may confuse you. Instead of this condition that d1, d2 divides mn, we have written d1 divides m, d2 divides n. What does this mean? What is the meaning of this sum and what is the meaning of this sum? The meaning of this sum is that actually you see, although you are writing d1, d2 here, but ultimately it's just this. You are going through all the positive divisors of mn, and for each such positive divisor you are writing a term, this term or this term, same thing. Now it turns out that all those positive divisors look like this, okay. And you have to also understand one more thing, that d1 and d2 are varying independent of each other. They are not, none of them is restricting the other one in any way. d1 is varying freely over the set of all positive divisors of m, and d2 is varying over the set of positive divisors of n. These two variations are independent. That is why instead of writing this, you can write this. You will get the same sum. But still, it may not be so clear from what I said just now. So this is what I suggest. You forget about this, whatever you have here, mu, omega, all these things. Lambda, omega. It is something, right? You take a specific m and a specific n, which are relatively prime positive integers. Take some small values. Say m is 3, n is 4, something like that. And you do not even write anything here, just write a star, because that star just remains star here, same thing. And then you calculate mn. Mn will be 12 for the numbers that I said just now. Say m is 3 and n is 4. They are relatively prime, so mn is 12. Now you write the sum for 12 in place of mn. And you know what the positive divisors of 12 are. All the divisors of 12, 1, 2, 3, 6, 12. Shall we have any more? But that's not the point. The point is that you calculate that sum. And by calculating the sum, I don't mean you calculate these things. You just see how many terms you are having in the sum and for which positive divisors you are having those terms. And then you separately calculate this sum, where m is 3, so you will be considering all the positive divisors of 3. Actually there are only 2, 1 and 3, because 3 is prime. Because n is 4, d2 will vary over the set consisting of 1, 2 and 4. How do you write this sum? This sum will have all possible combinations of d1 and d2 regardless of which one is coming with which, I mean everything will come. If when you take d1 equal to 1, for that all the 3 d2 values of 1, 2 and 4 will come, and for d1 equal to 3 also all those 3 values will come. That way also you get a sum. You see that you are actually going to get the same sum. That's how you can convince yourself that actually these two are same. Alright. Now because here d1 and d2 are varying independent of each other, and because all possible combinations are available, this sum actually is just the product of these two sums, which is a very easy thing to see. When you take the product of these two sums, all these terms will get multiplied with all these terms. Everything possible will happen, will come and give you this larger sum. But what is this? Oh, I forgot to mention one more small thing. In place of this, you can of course write 2 to the power omega of d1 times 2 to the power omega of d2, because your usual rule of exponent. So now what is this? This is just f of n, because d1 varies freely over all the positive divisors of m. Similarly, this one is f of n. So yes, you have got what you wanted to get. F of mn is equal to f of m times f of n. That means f really is multiplicative. So we write the conclusion of all this part. So f is multiplicative. That means our claim has been established. And now we come to our main task. We have to show that f of n is equal to 1 for all positive integers n. And in that direction, we first note this simple thing that f of 1 is 1. We have the f formula here, so let's see it here itself. F of m is this. So if m is 1, what will you have? The only positive divisor of 1 is 1 itself. That means the only value of d1 is 1. And accordingly, there will be only one term here in this sum, where m is 1, d1 is also 1. So you are having lambda of 1 times 2 to the power omega of 1. Lambda of 1 is 1, omega of 1 is what? How many distinct prime divisors does 1 have? None. There is no prime divisor of 1. So omega of 1 is 0. So you have 2 to the power 0 here. And accordingly, this is also 1, this is also 1. So that means this entire sum is 1. So at least for the value n equal to 1, f of n is really 1. Now next we consider the general case where n is greater than 1, and so it has a prime factorization. Okay, now what shall we do? And why did we work so much to establish that f is multiplicative? Yeah, now it will be revealed. In trying to show that f of n is 1, we will now simplify our task by not directly calculating f of n, but instead considering this. F of pi to the power ki, any prime power that you have here in the factorization of n, which by definition is of course this lambda of the number divided by d times 2 to the power omega of d, as d varies over all the positive divisors of the number, the input. And I guess you have already figured out how f being multiplicative will help us here. This is all we need to find. The advantage that this calculation has over the calculation of general f of n is this, that the positive divisors of a power of a prime are easy to figure out. You already know what the positive divisors are: 1, pi, pi square, pi cube, like that all the way up to pi to the power ki. These are the only positive divisors of pi to the power ki, and accordingly we can write the sum. So what will you get if you take d equal to 1, for example? Let us consider the positive divisors in increasing order. So let's first take d equal to 1. So this part will be pi to the power ki, and because d is 1, you have 2 to the power omega of 1. Then the next value of d is pi. Dividing this by pi, you get pi to the power ki minus 1 times 2 to the power omega of pi. Then the next divisor is pi square. Dividing this by pi square, you get this times 2 to the power omega of pi square, and continuing like that. Eventually, you take the divisor pi to the power ki minus 1. Dividing pi to the power ki by that, you get pi, and times 2 to the power omega of the divisor. And finally, you take the d value, which is this itself. Dividing this by itself, you get 1 times 2 to the power omega of the divisor. Alright, now, so in the next step, we use the lambda and omega values. Lambda of pi to the power ki by definition is minus 1 to the power ki. And when showing that our function f is multiplicative, we saw that omega of 1 is 0. So this is 2 to the power 0, so that is 1. This one is minus 1 to the power ki minus 1. What is omega of pi? Omega of pi is the number of distinct prime divisors of pi, which is 1, because that's just pi. So here you have 2 to the power 1, so that's why 2. Similarly, this one is minus 1 to the power ki minus 2 times 2, and it goes like this. Eventually you have lambda of pi, which is minus 1 to the power 1, so that's just minus 1 times, this is still 2, and finally lambda of 1 is 1 times, this is again 2, because this one is, the exponent is 1. And now here is a task for you. You have to now convince yourself, you think about it, that this is always going to be equal to 1. This I won't do. So we note this fact, that is f of pi to the power ki is equal to 1. And now finally we realize why the multiplicative nature of f helps us. Because f is multiplicative, we can write f of n as a product like this. The product of f of pi to the power ki, the f values of all the prime powers in the prime factorization of n. And just now we have shown that each one of them is 1, so the product is also equal to 1. So that's how in this case also, where n is greater than 1, we have proved that f of n is 1, and that completes the solution.